Hello everyone, and thank you for attending to this presentation. My name is Lucas. I'm a PhD student from France, and I will talk to you about our work, which concerns multi-resource scheduling applied to a graph of moldable tasks. In the literature, most models of scheduling problems only take into account one single type of resource, like CPU, except eventual additional communication costs between tasks. For instance, one usual scheduling problem consists of minimizing the total execution time for a graph of tasks, where the time required to execute a task only depends on the number of processors allocated to it. This problem is widely studied, with the best approximation ratio achieved so far being 3.42, 3 years ago by Chen. In this work, we extend this problem by taking into account multiple types of resources. Indeed, in practice, in high-performance computing, a large number of heterogeneous components are involved for a process. In particular, applications that require a lot of data may use appropriate architecture that should be taken into account while scheduling. For instance, CPU, GPU, memory, and cache could be 4 different types of resources that we may allocate to a task, whose execution time will depend on these 4 parameters. In another word, we consider that there are in fact multiple dimensions in our scheduling process. I will now explain how the multi-resources scheduling is modeled, with a small example consisting of 4 tasks with different resource types taken into account. For instance, we may use a computer with 4 sticks of RAM, represented by resource 1, and 6 cores, represented by resource 2. The time required for executing each of these tasks will depend on the number of cores and RAM you allocate to it, and one possible choice of allotment is shown in the table. A valid schedule will consist of the allocation combined with the starting dates of all tasks. Note that the precedence constraints need to be respected, so here it means that the starting date of task 2 and 3 must be later than the completion date of task 1. Also, we must have enough resources of each type to actually process it at any given time. One possible schedule is given at the right of this slide. More formally, we assume d different resources are relevant, each of them having p of I identical units of resource, and we are given n dependent moldable tasks whose execution time is represented by a function of the resource we may use, the function being fully known. We further assume that the execution time decreases if we allocate more resources for each resource type, but at most linearly for any resource types. For example, if we allocate twice as much processor to a task, the task may not be accelerated by a factor more than 2. So, in the last slide, I defined an instance of our problem, and now I will discuss what a scheduling algorithm needs to do. It must allocate for each task a number of resources of each type, and fix its starting date to minimize the make span, which is the total execution time. Furthermore, the algorithm must respect the resource and precedence constraints, which are already introduced in this previous slide. This problem is an extension of the special case with one single resource, and clearly it is NP-complete. For this reason, we will build an algorithm and study its effectiveness by computing its approximation ratio, which is a higher bound of the factor of error from the optimal for the worst possible instance. So this is a theoretical work, and our main results are new approximation ratios on several subtypes of this problem. In practice, we proposed an algorithm whose approximation ratio increases linearly with the number of resource types d, and that is equivalent to d towards infinity. But please note that this asymptotical result is purely theoretical, because usually d is small. And although not much work had been done before on this problem, the independent subcase was already studied, and our general ratio is asymptotically better than the pre-existing one, restricted to independent tasks. Yet we also improved our ratio for this specific subcase, even though it is still higher than this. But in fact, it might be difficult to find an algorithm with an approximation ratio lower than d, because any deterministic list scheduling algorithm with local job priority consideration may not be d. Moreover, in all previous studies of simpler subproblems with multiple resource types, for example unitary tasks with a single resource type, the best ratio was always at least d. So now I will present to you the algorithm before giving you an intuition on how to analyze it. Then I will conclude and present some potential future work. Before explaining the details of the algorithm, let's start by a few preliminary definitions. Two quantities related to an allocation are fundamentals: the area and the critical path. The first one, the area, corresponds to the normalized quantity of work that we execute over all the resources, the work being the number of resources multiplied by the time of the tasks. One way to see it is that if all the resources are used during one unit of time, the area processed will be d. Furthermore, the critical path is the length of the longest path in the graph. So these two quantities allow to bound the optimal time, because at best, all the resources are used during all the process, and the resulting time will be A divided by D, the area divided by the number of dimensions. Similarly, if we compute only the longest path, the processing time will be the critical path. Thus, the max of both quantities is a lower bound on the optimal time for a given allocation. So finally, Lmin of D, the minimum of the max over all allocation, is a lower bound on the optimal time, because we do need to choose one possible allocation. The purpose of the algorithm is to have a processing time as close as possible from Lmin. To do so, we adapted the algorithm from the two-phases approach first used by Turek in 92. The first phase is choosing an allocation for each task. The more resources you allocate to a task, the faster it will be executed. However, allocating too much resources may be a waste for efficiency, so we need to find the right balance. Once this is done, the algorithm simply schedules the task with no further modification for the allocation, which corresponds to phase 2. I will now provide more details for each of these two phases. The first phase is the allocation procedure. The goal is to find a trade-off between the execution time and the total work. It is then reasonable to first omit all the allocation that has both higher execution time and area, which corresponds to step 1. For the second step, we use linear programming to find the best trade-off between critical path and area, the two important quantities presented before. The idea is taken from the discrete time cost trade-off problem studied by Scutella in 98. Then we have to run the relaxed solution to a factor 1 over rho from the optimal for the critical path, and 1 over 1 minus rho for the area. The choice of rho may be arbitrary, whether we want to privilege area or critical path, and the best choice of rho will be shown later. The purpose of this second step is to link our allocation to the optimal time. Finally, we will adjust the allocation in step 3 so that a task does not take more than a fraction mu of a resource for any resources. Similarly to rho, mu may be chosen arbitrarily, but the analysis will provide an optimal choice. Phase 2 is much easier. We simply arrange the tasks subject to any priority rules, for example, longest job first, and schedule them whenever they are ready and there are enough resources to process them. In practice, we scan the list of remaining tasks anytime a task ends. With this two-phase algorithm, and by choosing mu is equal to 1 minus 1 over phi, and rho is equal to 1 over square root of phi d plus 1, where phi is the golden ratio, we achieved one of the claimed results. Okay, now that I introduced the algorithm to you, I will move on to the analysis. Of course, I won't be presenting all the details within 5 minutes, but I will try to at least give you an intuition on how to upper bound the approximation ratio and find the best choice of rho and mu. To do the analysis, we subdivide any schedule into 3 sets of time steps: I1, I2, and I3, depending on the number of resources used. The purpose of reduction is that if we are in I1 or I2, no tasks are ready because there are enough room to process any task, which means actually that the path lies in I1 and I2. Meanwhile, in I3 we are more efficient because we are sure that we use at least a fraction 1 over mu of the resource. So although reducing tasks may seem like a good idea, we are getting further away from the near optimal trade-offs that we computed before between critical path and area. However, we are able to bound this impact. Indeed, the time of any task may not increase by a factor higher than 1 over mu otherwise it would be a superlinear speedup. Similarly, the area may not increase too much. Yet even though this impact can be bounded for both time and area, if we reduce the task too much, the time and area might increase significantly, and the algorithm would just not be good enough. Yet we do need to reduce them to be able to split the schedule efficiently in the 3 intervals presented earlier. Similarly to ρ, this leads to a trade-off that we had to solve analytically. Indeed, to find the best choice of mu and ρ, we were able to find two bounds using critical path and area that we could merge together to obtain one final expression, valid for any choice of mu and ρ. Minimizing this equation finally gave the results. Let's finally move on to the conclusion. In this paper, we have studied the problem of multi-resource scheduling for moldable parallel tasks with precedence constraints, and have proven several approximation results. So for future theoretical work, we may try to close the gap between upper and lower bounds on the approximation ratios, but we might also try to evaluate experimentally the performance of the proposed scheduling algorithm. In fact, we have already built an in-house simulator handling multi-resource scheduling, but we have yet to find appropriate data and test it. So this is it for my presentation. Thank you very much. I am open for questions, if there is any. Thanks.